Hi, this is Professor Anil Kumar Sathe from Department of Mechanical Engineering, MIT School of Engineering, Pune. In this lecture, we are going to see work required in multi-stage compression. Let's say two-stage compression. So we are going to derive the equation for work required for two-stage. Just look at this figure. This figure I have explained you in the last lecture. So 0 to 1 is suction for first stage, 1 to 2 is a compression for first stage, 2 to 2 dash is intercooling between first stage and second stage, 2 dash to 3 is compression in second stage, and 3 to 4 is delivery at the end of the second stage to receiver tank. So compression of first stage is 1 to 2 and compression of second stage is 2 dash to 3. So work required to drive the compressor for two stage is given by W is equal to W of first stage plus W of second stage. What is W of first stage? Area behind the curve 1 to 2, because this is the compression process in first stage. And what is the work of second stage? Area behind the curve 2 dash to 3, because this is the compression of second stage. Why it is not this line? Because intercooling is there, means second compression starts from 2 dash and ends at 3. So W second stage is area behind the curve 2 dash to 3 and W first stage is area behind the curve 1 to 2. Now you know area behind the curve 1 to 2. This formula we are already knowing. Area behind the curve 1 to 2 is W of first stage, that I have put here. W of first stage n upon n minus 1, P1 P1 P2 by P1 raised to n minus 1 upon n minus 1. Now in the similar fashion, area behind the curve 2 dash to 3, 2 dash to 3, that is a second stage compression. It is written as n upon n minus 1 P2 dash P2 dash P3 by P2 dash upon raised to n minus 1 upon n minus 1. Just take the reference of this equation and apply the same equation for 2 dash to 3, you will get this expression. So by adding these two, we are getting the final expression like this. Now let's assume perfect intercooling. Just recall the example what I have given in last lecture. 25 temperature becomes 50 after first stage, and after passing through intercooler that 50 degrees Celsius temperature again becomes 25, means it is a case of perfect intercooling. So P1 V1, that means perfect intercooling means 0.1. Just look at the figure. 0.1 and 2 dash lying on the dotted line. This dotted line is PV is equal to constant, means isothermal process. See, 25 to 50 and again coming back to 25 means we have achieved isothermal compression. Means 2 is shifted towards left hand side, 2 dash, temperature drops again to 2 dash and that 2 dash is equal to T1. Means 50 is reduced to 25 and 25 is equal to 25. This is T1 and this is T2 dash. Both are equal, means these 2 points are lying on isothermal process. We can apply the law for isothermal process as PV is equal to constant. So we can write P1 V1 is equal to P2 dash V2 dash, and that's what written here. P1 V1 is equal to P2 dash V2 dash. So put it here, this P2 V2 dash is replaced by P1 V1 because of this isothermal perfect intercooling isothermal case is assumed. Now P2 dash is P2. This is also clearly understood from this. P2 dash is P2 because intercooling is a constant pressure process. So put that value here. P2 dash is P2. So P2 V2 dash is replaced by P1 V1. P1 V1 and P2 dash is replaced by P2. Again writing this expression like this by replacing, and you can see something is common out of it. N upon n minus 1 is common, P1 V1 is common, common is taken outside, and remaining thing I am writing in bracket P2 by P1 raised to n minus 1 upon n plus P3 by P2 n minus 1 upon n minus this minus 1 and this minus 1 become minus 2. So this is the expression for W for two stage compression. Now we will extend this derivation further to reduce the work to a minimum value. You know, work required to drive the compressor becomes minimum. That is always good because compressor is a power absorbing device. So in order to calculate the minimum work to drive the compressor, what we will do, this expression we will differentiate with respect to variable P2, because as you know, suction pressure and delivery pressure, suction pressure is atmospheric pressure and delivery pressure is the design pressure at which we want to design the compressor. So what is in our hand? To vary the P2. So P2 is the intermediate pressure. What is the intermediate pressure value at which value of W becomes minimum? So for example, I want to compress the pressure, compress the air from 1 bar to 10 bar, and I want to do it in 2 stages. I can go from 1 to 4 bar and 4 to 10 bar. I can go from 1 to 7 bar and 7 to 10 bar. I can go from 1 to 8 bar and 8 to 10 bar. Which case is the best possible case? So W should be minimum. So I want to find out the value of P2 at which W is minimum. So for that, what I will do, I will differentiate this W with respect to variable P2 and equate it to 0. For this I have made one simplification. I am going to put n minus 1 upon n is equal to x. After putting this, we are getting this expression converted into this expression. Just try it by on your own. Just n minus 1 upon n is put as x. So n upon n minus 1 becomes 1 by x. So we are getting this expression. Now differentiate this to get a minimum work with respect to variable P2 as I have already explained. Now see, dW by dP2 is equal to 0, d by P2, and in the bracket this expression. So that's what I have written here. Now 0 is equal to d by dP2. You can see only P2 is a variable, other things are constant. So 1 by x, P1, V1 are constant, that goes below 0 and becomes 0. So it is differentiation of only bracket term. So that's what I have written in this step. Now just carry out the differentiation further. Remember, P1 and P3 are constant, suction and delivery pressure. Only variable is P2. So differentiate expression with respect to P2 only. Other things are constant. So d by dP2, P2 raised to x, this P1 denominator, so I can write P1 raised to minus x plus P3 raised to x, P2 raised to minus x minus 2. Just differentiate this and equate to 0, you will get this expression. See, I will do it for first term. P2 raised to x, P1 raised to minus x. P1 raised to minus x is constant because P1 is not variable. P2 raised to x is what? What is the differentiation of this? Because P2 is a variable. X P2 raised to x minus 1 plus P3 raised to x is constant. What is the differentiation of P2 raised to minus x? Because P2 is a variable. It is minus x, P2 raised to minus x minus 1. Just shift the parameter. Keep P2 only on one side and P1, P3 on another side. Just do that effort. It's a simple calculation. X and x gets cancelled. And finally, you will arrive at the equation. You try this on the notebook. While trying, take care, P2 should be on left hand side and P1, P3 on the right hand side. Just shift the powers and finally you will get the answer. P2 square is equal to P1, P3. Just take a square root on both sides. P2 square root is P2 and square root of P1, P3. This is written here. So P2 is equal to P1, P3. What is intermediate pressure P2? It is a geometric mean of inlet pressure and delivery pressure. So this is the optimum value of a pressure at which W is minimum. So this P2 is equal to square root of P1, P3. I can write as P2 by P1 is equal to P3 by P2. Just look at this. Just do the cross product. P2 square becomes P1, P3. P2 square becomes P1, P3. So I can write P2 is equal to square root of P1, P3 like this. P2 by P1 is equal to P3 by P2. And this is called as pressure ratio in first stage as well as second stage. And both are equal in order to minimize the W. Okay. Now, this is the equation 1. You can see this is already known to you. This is the expression 1. And here onward we are trying to minimize the work. We are trying to calculate the value of P2. Now you have obtained the value of P2. This is the pressure ratio. P2 by P1 is P3 by P2, and this is the equation we have obtained. That is equation 1. Just put this value in equation 1. P3 by P2 becomes P2 by P1. After putting this, these two become same and it are added. These two terms are added. It becomes twice P2 by P1 raised to n minus 1 upon n minus 2 as it is. And this becomes twice because P3 by P2 and P2 by P1 are same. So it becomes twice. Other things are remaining same as it is. Now I will take 2 common from here. Now expression becomes like this. This is for 2-stage compression when x is equal to 2. X means number of stages. Now I will generalize this expression for number of stages. X is equal to 3, x is equal to 4 or x is equal to x. So W, this expression is for 2 stage. You can see here 2 is coming. If I have to write the same expression for x stage, I will replace simply 2 by x and this is as it is. So W is equal to x means number of stages into, just look at this expression. This expression gives you the work required for a first stage of compression. So when perfect intercooling is there and when work is minimum, then work required for multi-stage compressor is calculated by W is equal to x, that is number of stages, into work required for a compressor to drive first stage. So W is equal to x into work required in any stage of the compressor or first stage of the compressor. So it's a simple expression. For example, 3 stages are there. I am going to put the value of x as 3 and this is the work required for a first stage compressor. So this is the end of the expression for work required for multi-stage of the compressor. Thank you. In next lecture, we will see what will be the value of pressures when intermediate pressures are more than 2. In which case more than 2 intermediate pressures are coming. 3 stages, 4 stages, 5 stage compression. P2 is an intermediate pressure for 2 stage compression because P1 is suction and P3 is delivery. P2 is intermediate. If there are 2 stages, P1 is suction and P4 is delivery. If there are 3 stage compression, P1 is suction, P4 is delivery and P2 and P3 are intermediate pressures. If there are 4 stage compression, P1 is suction and 4 plus 1 means P5 is your delivery pressure and intermediate pressures are 3 in number, P2, P3 and P4. So how to calculate if there are more than 1 intermediate pressures, means 3 stage, 4 stage, how to calculate the intermediate pressure, that we will see in the next lecture. Thank you.